transformation is a function between two vector space that preserve vector addition and scalar multiplication in simple terms, in a rule that transforms one vector into another in a way that aligns with the structure of the vector space. These transformations are not just theoretical, they help us understand how systems behave when subject to change, whether in engineering, physics, or data science. Understanding the kernel and range of a linear transformation is especially important. The kernel tells us which vector get mapped to 0, offering insight into the internal structure or loss within a system. The range shows us all the possible outputs, essentially what the system is capable of producing. This concept are critical in real-life applications such as 3D graphics, rendering signal processing, solving system of equations, and even in machine learning algorithms where dimensionality reduction techniques.
So now, I will explain about concept of kernel. For the first one, definition kernel 1 of 3. Kernel is the set of all input vectors that are mapped to the 0 vector. So to be understood, we can let the V to W be a linear transformation. Then, the set of all vectors V in V that satisfy T in bracket V equals to 0 is the kernel of T and is denoted by KER T. In other words, the kernel is the set of all input vectors that are mapped to the 0 vector in W. So for the second one is kernel 2 of 3. By theorem 6.3, the kernel is a subspace of V. The kernel of a linear transformation can be understood by T. V to W is a subspace of the domain V. This means it includes the 0 vector and is closed under vector addition and scalar multiplication. Lastly, the concept of kernel 2 of 3. By theorem 6.3 corollary, we can let T R power of n to R power of m be the linear transformation T in bracket S AS. Then the kernel of T is equal to the solution space of AS equals to 0.
Hi everyone, I'll be explaining the range of a linear transformation. Let's begin with the definition. The range of a linear transformation, T is a linear transformation of vector space V to the vector space W. So it is the set of all output vectors in the codomain W that you can get by applying T to the vectors in the domain V. So symbolically, this is written as below. So this simply means the range contains all possible outputs of the transformation. Now here, what it represents. Imagine a transformation like a machine. You feed in inputs from the domain V and it gives you output in W. The range is the collection of all outputs that can actually be produced by that machine. It's important to note that the range is always subspace of the codomain W.
Okay, now let's go through the full example to understand how to find the kernel and range for a linear transformation. Consider matrix A 2 by 3 matrix representing a transformation from R3 to R2. To find the kernel, we solve the equation AS equal to 0. That means find all S in R3 such the transformation sent them to the 0 vector. This gives us a system of equation. Let's simplify it step by step. From the second equation, we get x2 equal to negative x3. Substitute into the first and we find x1 equal to x3. So the solution is scalar multiplies for the vector 1, negative 1, 1. That's our kernel. The kernel is set of the all vector that map to 0. It forms a line of R3. Now, let's find the range. The range is column of space A, the span of each column. Notice that column 3 is a combination of others. So, only column 1 and 2 are linearly independent. They span the range. The range is spanned by two vectors in R2. So, the transformation is on 2 and the range is plane in R3. To summarize, we solve AS equal to 0 to find kernels. and identify the column space as the range. Let's pass to the next speaker for the conclusion.
In the conclusion, from the example, we found the kernel by solving the homogeneous system, which gave us all vectors mapped to 0. The range was determined from the column space matrix, showing us all possible outputs vectors. This example can demonstrate how linear transformations reduce, preserve, or eliminate information depending on the structure of the matrix. Kernel and range help us to understand the structure, behavior, and the efficiency of linear transformations, showing us how input are mapped, where the information is lost, and whether every output can be reached. They are essential for solving systems, analyzing dimensions, and building a foundation for advanced application in mathematics, science, and engineering. Islamic perspective, Surah Al-Qamar ayah 49. A'udhu billahi minasyaitanir rajim. Innahu kulli syai'in khalaqnahu biqadar. Meaning, indeed, all things we created with precise measure. It means that kernel and range show us how mathematical systems behave in a structured and predictable way, just like Allah's creations.